Hello, everybody. I am Luis Fernando. First of all, I would like to thanks IEEE and the ARGENCON committee for the opportunity, and thanks the friends of Argentina and Brazil. Um, the work has development by me and the Benjamin Galvão, the engineer Benjamin Galvão. Um, I and Benjamin are from IBBX company. The IBBX a startup company. We focused in apply electromagnetism, um, and and the principal research in the company is the electric small antennas and the low frequency. Okay, okay, let's go. Um, well, the objects of the work for me is three. First, the proof of concept uh, of the RF energy harvest system, low frequency band, apply to low power wireless device, because the system have low cost, have less susceptible to interaction with the environment. um, Secondly, the studies and the experiments to obtain at least 10 milliwatts DC at 1 meter from the RF source, because the sensors that our use um, I use are industrial sensors that use 1 milliwatts. So 10 milliwatts is the 10 times that necessary for the working the sensor. Of course, for working in this area, a low frequency band, um, I need to understand behavior, the small antennas in near field and far field. Okay, so these 3 points, the objectives. For development this work, I development two indoor system, one system operating in 1.3 megahertz, and the system two in 150 megahertz. Okay, this in show, this in figure one in show is basically 1.3 system. Okay, this figure two is basically 100 megahertz system. I in next slide I explain the circuits. Okay, in slide in figure three, um, I present the setup of the test indoor. The setup, the two antennas are on the wooden table. Okay, these these antennas is moved in 1, 2, and 3 meter. Okay, um, this imaging present the setup in 1.3. You can see that the two antennas is electric small antennas. Okay, the system components that I use for the power sources is the T transmitter in 1.3 megahertz, like I I explained. Um, and the power transmitter is adjustable up to 10 watts for 1.3, and the adjustable in 5 watts for 150 megahertz. Okay, the receiver is same difference, some difference, because the two antennas are electric small antennas, um, and the middle line antennas. The one, just one difference in the impedance of the first system. We have matching the impedance in 15 ohms. Okay, because it is conventional mode. And the impedance of the two antenna is 377 ohms because it is the same impedance of the wave in far field. Is it two prototype using in our work? Okay, this prototype one is the 1.3, the prototype 2, 150 megahertz. The prototype 1, the very point of difference is the ferrite system. Okay, the ferrite system here working like matching for the system, but also like antenna because it capture energy too. Okay, the other system have the R inductor R nucleo of the R nucleo and the capacitor filter and the supercapacitor in the storage. Okay. Basically, the receiver have 4 blocks for working, okay? The block 1, the rectifier, RF-DC converter. The block 2, control and charge management circuit. The block 3, storage capacitor. And the block 4, the load, or like a wireless sensor. The block 2 is very important. I am going to explain more about this circuit in next slides. Okay, now I am going to explain about the results and the measures. Okay, this equation is very important because she be in reference 3 in work with the Professor Hans, the very good work. This equation is special because he calculated the power receiver in near field. That is very different to far field. Okay. In freeze, for far field, I will use the freeze equation in conventional mode. Okay, for not having interference of the others equipments like cables of the multimeters, I use this method developed inside the IBBX for the measure of the energy, storage energy. Okay, this method is very useful, very simple, because we have four steps. Okay. The step 1, discharging one supercapacitor, 1 Faraday time 35 volts, discharge the capacitor to 0 volts. Okay, confirmed 0 volts. In 2 step, the RF source is on and charging the capacitor during 1 minute. Okay. The step 3, the voltage in the supercapacitor has measured. Okay, is the charge is calculated using the expression here. Okay, for to confirm the energy, the capture energy, the supercapacitor has connected to, for example, 15 ohms load. Okay, is the time is charged, the time of the discharge is measured. Okay, is you can have the confirmation, the energy storage. This is the management circuit. Okay, this point is important because is difference entre system 2 and system 1 is that the supercapacitor is charging to voltage, ideal voltage, and the management circuit control the switch. Okay, when the U ideal is goal atinged, the capacitor is switching, okay, in the load, okay. The two system, in addition, also have the measurement circuit of the switch, the supercapacitor, but in addition, I make the converter buck bus, the special converter buck. This buck maintain the voltage constant, for example, 1.2, 4.2 voltage, and they limited the current for transfer the more energy possible. Okay, this is results of the indoor tests. Okay, in 1, 2, 3 meters. Okay, this table 1 show the results of measures. The table 2 is the results calculated. Okay, you can see that's very close, the two values, the two tables. Okay, this is the gain we use for the calculated. Okay, this table in blue is very important table in the work, because this table show that in 150 megahertz is the very high level of the energy storage. Okay, if compared with the 1.3, I have the very high level in 1 meter, 10 milliwatts, 2 meter, 6 milliwatts, 3 meter, 2 milliwatts. Is very good, because our sensors work in 1 milliwatts. In addition, I have the effect of the hands in the system. Okay, you can see that is negligible. Okay, it's very good results. And for the test, final test, I make the testing outdoors AM broadcast station, né? Make harvesting the energy, radiating energy. Okay, also the very good results. Okay, this broadcast is operating in 1.55 megahertz. Okay, is the name Radio Cacique. Oh, well, the conclusions for me is three. That slide for me is more important slide of the presentation, because show like I need study more the electrical antennas and the near field, but in 3 points, the conclusion is the proof of concept has demonstrated by experiments is possible captured 2 milliwatts in 3 meters. Okay, for using wireless sensor, for example. But the second point, very important, because it's necessary to study deeply the behavior of ESA antennas in near field. This is very important. The 3 point, of course, many ideas of improvement after efforts. Okay, like improve the ESA antenna design using new methods, improve the conversion RFDC circuit to have a better efficiency, look for a new approach to analyze the capture of the energy, improve the methodology of the measures, understand better the measured results in near field. Okay, Our contributions, I like that this work to present another possibility of wireless power transfer in low frequency, okay, in near field, because the others working in high frequency and far field, okay? To disclose the results of the experiments to be discussed and to talk about the difficulties during development, and in finalizing to open discussions about the optimizations concerning topics with the project improvement of ESA designs, RFDC, power conversion circuits, use of new materials, and others. Okay, this is our reference. Okay, very good reference. And in finalizing again, thank you very much for your time. Thank you IEEE, thank you ARGENCON committee, thank you all. And this ended the presentation.